My name's Grant Bugher, and I'm here from Microsoft to talk to you about the secure use of cloud storage. So a little background on myself. I work at Microsoft in online services, security, and compliance. So I work with the product development teams that are creating Microsoft sites and services and help them to develop secure software and securely deploy their infrastructure. And just as throughout all of industry, teams at Microsoft are considering using cloud services, and Microsoft has its own cloud offering as well, Windows Azure. And so I've been pretty heavily involved in that lately. So I'm going to talk about a couple of cloud storage systems and applications written against them. So the two I'm going to be discussing are the Microsoft Windows Azure platform and the Amazon Web Services platform, as they're both mature cloud storage platforms which are being used by companies today. They also have well-documented interfaces and are good for doing research on. So I'm also going to do a bit of a talk about database attacks on cloud-based applications and walk through how people carry out injection attacks on a cloud-based app. And then I'll move into defenses and mitigations. How can you develop your software to not be subject to these attacks? And how can you design more secure applications for the cloud in general? So really, this information could be useful to software designers, architects, testers, anybody who is designing, building, and deploying applications. I'm really focused on the development side, writing new applications for the cloud, and want to help you understand the security challenges and the recommended approaches to designing and developing more secure apps in the cloud. So cloud storage systems. The purpose of these systems is to move the application database layer to the cloud. So rather than running your own databases as your backend, you can use a cloud storage platform run by someone else as the database backend. And you can actually use a cloud storage system regardless of if you are writing a cloud application. You could host your storage layer with Microsoft or Amazon while still running your own app, or running your app on traditional hosting rather than actually hosting your app in a cloud system. The storage layer is actually separate from the processing layer. Cloud storage promises very high performance, scalability, and availability. It's the reason people use it. You can store enormous amounts of data, pay only for what you're storing, and have the performance remain constant as the amount of data increases. Cloud storage systems are designed to handle a variety of types of data, including blobs, tabular data, queues, and even relational databases. And I'll be talking about how Amazon and Windows Azure handle each of those data types. So whoops, I think I went the wrong way. No, OK. So the Microsoft Windows Azure platform has two storage services. The Windows Azure Storage Service, which is divided into a blob service, a table service, and a queue service, and SQL Azure, which is a relational database in the cloud. Amazon Web Services has the Simple Storage Service, which is type of blob storage, SimpleDB, which is tabular data, roughly akin to what the Azure Table Service provides, and the Relational Database Service, which once again is relational database hosting in the cloud. So the Windows Azure Blob Service is designed to handle large arbitrary binary objects. They don't actually necessarily have to be large. You could store images, style sheets. Pretty much any single block of data can be stored in the Blob Service. They are designated by a container name and a blob name, which are roughly akin to a folder and file name. Containers can be very large, and the containers and blobs can have associated metadata. So not only are you storing the blob, you can attach metadata to it, which can either be things like the date it was uploaded and such, which are added automatically by the platform, or you can add arbitrary metadata to blobs just for your own use in indexing and finding them. Containers can be public or private. If they're public, anyone can access them. And actually, if they're public, it's possible to access them directly in a browser. So you can, for instance, host your static content from a website, the images and style sheets, and have people download it straight out of the cloud provider and not pass through your server at all for that static content. In addition, public blobs are supported by the Windows Azure Content Delivery Network, so they have a worldwide set of servers for distributing these. Blobs in private containers require what's called a shared access signature to access. So essentially, your request needs to be signed in order for you to get anything out of the private container. Generally, these are used as back-end storage by applications rather than having end users access them directly. But actually, I'll be going through some scenarios where you do want end users to directly access side containers. The general API is a REST API, representational state transfer. So essentially, it's stateless. You make a call to it with a URL and some attached headers, and it sends back the blob. The Azure Table Service is designed to handle arbitrarily formatted tabular data. So it's kind of interesting. People refer to it as a table, but it's not like the tables you're used to from a relational database, because each row has a series of named properties, and there's no requirement that the rows in a single table have the same properties. So you could actually have different columns on every row in the table. And it's not storing empty values for other columns. Those columns don't exist. The set of properties is actually a property of each row and not of the table. A table can be very large. It can hold billions of rows, terabytes of data, but they are not relational. There is no concept of a foreign key constraint in the Azure Table Service. The only constraint is the uniqueness constraint on the key to each row. The table service is managed and accessed through an XML-based REST API. Special headers are required, though, so you can't access Azure Table Storage in a browser the way you could the blob service. It's genuinely meant to be an application's data backend and not accessed directly by end users. In addition to the REST API, Microsoft provides a WCF Data Services API for ASP.NET developers to access it in a familiar way. And that has some security advantages as well that I'll get into. The Azure Queue service is kind of interesting because it's not what people normally think of as storage. It's a queue of very short binary messages. They're limited to 4K each. And you have APIs to put a message in or to mask or remove a message from it. What this is actually for is when you are hosting your entire app in the cloud, and so you have an arbitrary number of nodes all running your app, and they need to communicate with each other. You can use this. You can use a common queue among all of them and have this do messaging between them. Once again, it's a REST API. Special headers are required. You can't access it in a browser. And it's not intended for storing data at rest. It's meant for communication. In fact, by default, after 7 days, messages expire and just go away if you haven't taken them out. Finally, SQL Azure is a true relational database service in the cloud. It's based on Microsoft SQL Server 2008. It's accessed just like SQL Server 2008 with the tabular data stream protocol, which is the protocol on TCP 1433 that all SQL servers use. It supports tables, indexes, views, stored procedures, constraints, triggers, most of the things you'd expect from a SQL database. About the only things you don't get are the service broker, SQL reporting services, SQL analysis services, and the distributed transaction coordinator, because the distribution and clustering is under the control of the service and not you as the developer. You can use any Microsoft SQL Server client library to access this. You can even use the SQL Server client tools like Management Studio and Visual Studio. So moving on to Amazon's web services, S3 is the simple storage service. It stores arbitrary binary objects. They're referred to as objects and the containers as buckets, so there's different terminology. But once again, the objects can be very large. They have associated metadata. You can make them public or private. And objects in public buckets can be accessed with a browser. And public objects are supported by a content delivery network, which Amazon calls CloudFront. SimpleDB is a table service. Stores arbitrarily formatted tabular data. Once again, very large amounts of it, terabytes of size in a single table. They are not relational, and they are, once again, a property with a series of named attributes. So each row in the table, they're referred to as entities, has a series of named attributes, and there's no reason you couldn't have every row have different attributes in a table. Really, both this and the Azure Table Service are referred to as table services because that's the primary use people have for them. Just because you can put different properties on each row doesn't mean people usually do. It's usually used to represent tabular data. Amazon's table service can be managed and accessed through REST or SOAP APIs. The REST API is potentially accessible from a browser. The SimpleDB requests can actually be condensed into just a URL. So unlike with Azure Table Service where you have to specify custom headers, with SimpleDB you could in theory get it out of a browser. That's just not the intended use of the service. They provide Java and .NET SDK binaries for easy access, as well as a WSDL for a SOAP API, so that if you have any SOAP toolkits or Visual Studio or whatnot, you can import the WSDL and create your own interface classes. The relational database service, it's a true relational database service in the cloud. Amazon's is based on MySQL. And it has full support for the standard MySQL features. It uses MySQL's client-server protocol, and you can use the standard Windows or Linux MySQL libraries to access it. It's pretty much indistinguishable. Both SQL Azure and the Amazon Relational Database Service are functionally identical to standard non-cloud database hosting. So as a result, I won't be talking much more about those in this presentation, as the security risks with those are pretty much the same as you would get from any SQL-based backend. So injection attacks. Injection attacks are the most common threat we see against databases in the online services world. Injection attacks, the most common is SQL injection, of course, where you put in some data that gets parsed into a SQL string and sent to the database and executed. The database layer, though, in traditional hosting is not generally exposed to the internet. The database layer is somewhere on the back end where only your app can reach it. In the cloud services world, this actually isn't true. Your database layer is sitting on the internet. However, if your access control is set up properly, it should be just as inaccessible to an attacker as it would be in the back end. It requires cryptography and so on to actually access. So your main way of attacking the database layer is still via carefully crafted malicious input, something that looks like data to the application, but is executed as instructions by the database. Rather than SQL, most of the injection attacks we can try to come up with on a cloud service are actually based on XML and their REST APIs instead. So XML and XPath injection. Everybody's probably familiar with SQL injection, but XML data and XPath queries are also subject to an injection attack. It's the same issue as with SQL, fundamentally. It's a form of mixed code and data. XML contains both the data values, but also what data items and schema that they go into. And XPath contains both the query structure that tells where you're looking, as well as the actual items you're looking for. So if these are constructed from strings, you potentially get the same risks for injection attacks. On the bright side, with XML data, they often use smart serializers. People often don't construct their XML from strings. Rather, they use an existing XML serializer class, which hopefully has been better tested against these sorts of attacks, but not always. Unfortunately, with REST interfaces, they're so simple that especially on small or simple applications, developers do sometimes construct XML from strings, rather than going through the overhead of using an XML serializer. So there are two basic kinds of XML parsers, SAX parsers and DOM parsers. So SAX is the simple API for XML. It's a unidirectional event-driven stream parser. That is, it starts at the beginning of the XML file, reads each node one at a time, beginning to end. It's very fast, low-memory serial processing. The memory requirements don't grow with the size of the XML file. And it interprets objects as it goes along. There are not really any standards for the behavior of a SAX parser. The Java parser is considered normative. Whatever the Java parser does, that's pretty much what people think a SAX parser should do. DOM parsers, on the other hand, construct a full in-memory representation of the XML document. So they create objects to match with all these nodes and values. It takes more memory, and the advantage, though, is it's fast for random access. With a SAX parser, you have to do everything you're doing with the XML file as you go along. With a DOM parser, once you've loaded the DOM, you can access anywhere in the XML file very quickly. It allows random access to nodes. The thing about the DOM model, though, is DOM level 3 is a formal W3C standard. So all DOM parsers should at least theoretically act the same way. So an example of XML injection. Here we have an XML data item. It's got a username, an email, a password, a user ID, a group, and a password hint. Against a SAX parser, I could actually inject against this by simply, in my password hint, closing the hint tag and throwing in an additional value for one of the previous ones. For instance, I could throw in another UID and overwrite the previous one. Since the SAX parser is reading serially, later values will replace earlier ones. In a DOM parser, on the other hand, I might have to be a little more clever. In this case, I'm using an XML comment tag in one field I've injected into to comment out XML that's between that field and the next one. This way, when I go adding additional tags in my password hint, it doesn't have a collision with the previously assigned values. A DOM parser doesn't like XML that is not fully compliant. If you have the same value repeated more than once and the schema doesn't call for that, it won't parse it. So you have to be a little more clever to get past DOM parsers, and frequently to carry out an injection attack, you need to be able to inject into two fields. So attacking cloud storage applications. Amazon Web Services and Microsoft Windows Azure both use a wide variety of interfaces, but these interfaces are web services, and they are thus based on text strings. SimpleDB query strings are actually written in SQL. Azure Table Storage query strings aren't written in SQL, but it is a query language which is roughly akin to what's in the where clause of a SQL statement. The Amazon Web Services SOAP API is XML-based. You're passing blocks of XML back and forth. And the Azure Blob Table and Queue Storage APIs are all XML. Even the requests are sent in XML, unless you're doing the simple URL-based blob storage retrieves. REST and SOAP interfaces are very popular for web services. While I'm just looking at Amazon and Azure in this talk, I imagine most other cloud database services, as those come into being, will probably use the same sorts of interfaces. I think we'll see these same problems with pretty much any app using cloud storage. Text strings are potentially subject to injection. So there are a variety of approaches we can take to try to attack an application that we know is using cloud storage. There's query string injection, where we attempt to modify the query string in a read. Direct node injection, where we try to inject XML straight into their XML API. DOM injection, doing the same thing. Persistent cross-site scripting. This isn't really an attack on the data layer, but I've seen applications trying to mitigate data attacks open themselves up to persistent cross-site scripting attacks. Storage enumeration is rather different from the rest of the things I'm talking about here, because it actually happens when you're trying to make files available to the public and have external users attached to your cloud storage directly rather than using it as a data backend. And finally, account level and infrastructure attacks. Since the database is sitting on the internet, if you don't properly protect the accounts in the database, it's possible for an attacker to actually directly connect to the database. The thing that's interesting here, all of these attack applications and users of cloud storage. Nothing I'm talking about today relies on any vulnerability or bug in either Amazon Web Services or Windows Azure. They, as far as I can tell, are implemented properly. Now, on the bright side, it's good that they've paid a lot of attention to security. Unfortunately, that means there's nothing to patch here. The things I'm talking about are things that developers are going to need to face as they move into cloud storage. So query string injection. Amazon Web Services SimpleDB uses SQL-like queries to query the tables. It's select attributes from domain, where conditions, with an order by and a limit optional clauses. The entire string is one parameter that gets sent to the REST API. So since this is one parameter sent to the API, things like the SDK aren't going to be doing anything with this parameter. You as the developer are responsible for assembling this parameter from strings and passing it into the API. The Azure Table Storage query string, as I've mentioned, is not SQL-like, but it is still one parameter, a string, encoded as a unit, and potentially subject to its own kind of injection attack. So since the query string is a single parameter, the onus is on the app developer to prevent injection. SimpleDB query strings support multiple quotation types and don't require escaping for one quotation type enclosed in another. It's kind of like how PHP works, where if you want to put single quotes in a string, you can enclose the string in double quotes. The single quotes have no meaning in there, and they won't escape out of the string. An attacker who can control input to multiple fields thus can change the semantics of the query. So an example of how this could work. So here we have a simple query string. Select from products where category equals my category, intersection access equals public, order by column name. So in this case, I've got a set of products, some of which I display to everyone, some of which are private or access controlled in some way, and I'm letting the user sort and choose what category they're looking at. So I've got some access control mixed into here. This is not a good way to design an application. If I give malicious input with, say, some single quotes and double quotes in it, in this case, I've given an input of my category quote or category equals double quote and a sort order. Sort order would obviously not be typed in by the user, but sort order is often inserted by JavaScript when someone clicks a column header and sent back to the backend application. Well, if you're inserting with JavaScript, a user with an HTTP debugger can insert whatever they want there, and so they can insert arbitrary strings. Well, if I take that string and pass it back to the database as a query string, it's going to be interpreted this way instead. That's the same string with different highlighting. I'm now saying the category has to equal the one they selected, or the category has to equal a bunch of junk strings, where I've just taken the access control out. And then I order by column name, so now I'm getting all data items rather than just the public ones. So the presence of multiple quotation types can allow users to insert or elide fields from the query. And the mitigation for this is identical to that for SQL injection. Validate user input, make sure there's not malicious input in it, and encode values before constructing a query string. The bad news here is there's no equivalent to parameterized queries. You as the developer have to construct the string. There's no way to have the API do that for you and avoid these sorts of problems. On the bright side, there aren't that many meta characters to encode here. Since you're sending data to the database backend, you're generally not worried about a lot of globalization and Unicode issues and so on. Though depending on your application, you potentially could be. The good news is that query strings only issue queries. You can't take one of these, and in SQL, for instance, you could have or rather on a traditional SQL database, you could put in DDL, things like dropping a table, or putting in code to modify table schemas, to add users, and so on. There's no equivalent to that in these query strings. A query string in SimpleDB issues queries. It's a select query. You can't change reads to writes. You can't do other operations. All you can do is change what's being read. There's also no equivalent to CLR stored procedures, PL SQL, any of these other ways of executing code on the database. It's just reads. And since the verb is found outside of the query string, you can't do an insert or update or delete, because the way you do those with SimpleDB requires changing the REST call and not just changing the query string. So it's not as necessarily harmful an issue as a SQL injection in a relational database would be, but it's still something to consider. So XML injection. Windows Azure storage interfaces are XML sent over REST. And XML interfaces can also be subject to injection. It's less familiar than SQL injection. But here, since we're injecting directly into the API of the cloud storage provider, it is possible to do data writes and DDL-like operations. When I'm going through some of these examples, I'm not going to make assumptions about the SDK or API used. It's true that with Windows Azure Storage, most of the users of that are also using Windows Azure hosting, and thus they're writing in ASP.NET, and they're using Windows Communication Foundation. There's a lot of layers between them and the application. However, you can use Windows Azure Storage from any application. You can use it from a simple PHP application. It doesn't have to be hosted in Windows Azure. It could be hosted anywhere. So we can't make those assumptions about what kinds of interfaces are being used. The only way we can know what mitigations are in place is to try sending input to the program and seeing what happens. So here we have an attempt at a direct node injection. As I mentioned with SAX parsers, you can overwrite earlier values with later values. This was the first thing I tried, trying to attack a applications database layer. In this case, I'm going to use for an example on a lot of these a simple blog commenting and blogging application that I threw together in .NET. We have a title, a user ID, which is who posted it, an avatar URL, which is their user icon, and then the text of their comment. In this case, my user's comment text closes the comment text tag and then tries to overwrite user ID. That doesn't work. The parser's too sophisticated. The platform protects from this sort of attack. Even if I connect to the data endpoint directly and send this, it doesn't work. If you have duplicate nodes or any kind of schema validation errors, it invalidates the whole API call. You don't even get an error message. You get 400 bad requests with no other data provided at all. So this tells us we've got a DOM parser here. Thing about DOM parsers is DOM parsers are smart, and that makes them difficult to write. And as a result, they are generally very standardized implementations. Everybody uses the same few DOM parsers. So smart parsers usually implement the full XML specification. The fact that they implement most XML tags indicates they probably implement almost all of them. This includes things like XML comments and also block encoding with CData. CData is a special tag in XML which, once that tag opens, it tells it everything in the document until the CData closing tag should be considered a single blob of data. So no matter what XML meta characters are in that, carriage returns, binary data, and so on, it's all treated as a single unit and doesn't change the schema of the file. Everything until the closing tag, which is 2 right square brackets and a right angle bracket. So introducing these tags by an injection attack may allow modifying the XML. The advantage of these is we can change the meaning of the XML without introducing duplicate tags or messing up the XML structure. We're still going to have an XML file that is valid and parses without errors. Now, unfortunately for attackers, and fortunately for us, this actually has some drawbacks. It introduces junk into one or more tags. The problem with using XML comments and CData blocks is you don't have a way to get rid of those CData and comment opening and closing tags. So as a result, sometimes this stuff's going to be visible to users and so on, and not as hidden by the attacker as they might like. On the other hand, sometimes you can inject into fields that never display, and this actually isn't a problem at all. So here we have my same blog comment engine example, and in this case I've injected an XML comment. Assuming this is constructed from strings, if I can get an XML comment tag into my title, close it in comment text, I've elided some fields, and thus I can put in new replacement fields and not break the XML. It'll still parse correctly. In this case, what I've done with my new replacement fields is I've changed my user ID. So I'm now posting as a different user rather than as who I'm logged in as. I could do the same thing with a CData tag. In this case, I've got an opening CData tag in my title, and I close it in my comment text. The disadvantage there is this is a case where it's going to show to the user. That massive block of XML between the opening and closing CData, that just became the title of my blog comment, which is probably not, as the attacker, what I intended. However, with this particular XML structure, I don't have a choice if I have to use a CData tag to bring things out. I'm stuck with junk data in one of the tags. Those were demoed against Azure. There's no reason you couldn't do the same thing against SimpleDB. As you can see, this is a different XML schema. This is actually the contents of the SOAP envelope in a SimpleDB call. But it works the same way. The XML schema is different, but the principle is the same. So persistent cross-site scripting. When we're faced with these attacks against the XML data layer, people often turn to encoding to prevent XML attacks. So when I put in that XML comment or that CData tag, they get munged by the encoder into encoded values which don't affect the XML schema. Seems like a good way to prevent my XML attacks. But that's not the only thing people use encoding for. Encoding output is also used to prevent cross-site scripting. So if somebody submits some script, the end user's browser doesn't render it as HTML and execute the script, but rather just represents a visual version of it. The problem is these encodings don't substitute for each other. And I have seen cases where developers think, well, I'm using encoding, and therefore I'm safe. But the encoding you're doing for storage is completely different from the encoding you're doing for user display. There are different layers. And the encoding you do on data storage is reversed before the data is output. So the problem you can run into is things like this, where I've got an encoder that's stripping out angle brackets and that sort of thing, but not worrying about other values. And so I've stored in my database an encoded cross-site scripting attack. Now, when it goes to display to the user, well, it pulls it out of the database, it reverses the encoding. Re-encoding it never did, because the attacker did that encoding, and essentially weaponizes the data in the database. So just when using encoding, it's important to be careful to remember what encoding you're doing and make sure that you reverse what you do and not what other people are doing. So I'm going to switch gears a bit to a different use of cloud storage and the vulnerabilities that can introduce. Not all attacks on cloud storage involve application bugs. One thing that people use cloud storage for is storing public or semi-public files for end user download. It's a natural fit for cloud storage. There's massive storage capacity and cheap scalable bandwidth. If I want to host, say, video or audio content for my end users to download, I'd love to be able to put it in my cheap scalable cloud storage and allow my users to download directly from that store. The problem is that when you have a subscription-based site, you can run into some difficulties with this. The files, after all, are hosted on the cloud provider. They're not hosted on your web server. They're not part of your application. They're not behind your application's access control. You may have an htaccess file or various cookie-based authentication and so on your app, but once somebody actually clicks on the file in cloud storage, they're getting redirected over to the cloud storage engine itself and pulling the file down from there. So that's not behind your access control. What sites often do with subscription sites, I've mainly seen this with sites that are selling ebooks and instructional videos and various informational content. It's very popular for affiliate marketing businesses and so on to sell information products this way and host them in cloud storage. So what they often do is they resort to security by obscurity. They put all of their files on the cloud storage engine, and then they give their containers or buckets a really long hexadecimal name or just a name they don't publish out to the users, and they hope nobody will find it. And then they only put the links inside their own site behind the access control. This is also a problem when it comes to sites with tiered access levels. What enumeration is I've got all this in cloud storage. If I get one of those URLs, I now have at least that file name or the container name, and I can connect to the cloud storage system itself and download the file or even ask it what's in the container and get all the other files as well without necessarily going through the site access control. It's not just sites that are subscription-based that run into this, but also sites that are multi-tenant or have tiered access control. Because if I'm storing everything in the same back-end bucket, once somebody has the URL for one of my files, they can then enumerate it to get the URL for other files. So I'm just going to give a quick demonstration of how easy this is. So this, you probably can't read it due to the size, but this is an easily available on the internet tool called S3 Ripper. And it's a simple matter of You go onto a website that's using cloud storage, you hit view source and see what all their cloud storage URLs show. A lot of times the subscription-based content that's behind the access control and the images and style sheets on the homepage are in the same bucket. So the bucket name is right there in the source on the homepage. And you type in the bucket name and click Find Files and Folders. And I'm not connected to the network. Okay, live demos never work. I should know better than to try to do that. In any case, it will list every file in the entire container along with the file type, date, file size, and you can download any of them or even click a download files and it will promptly download everything in the entire container to your computer, thus duplicating everything that they have on their server in their cloud storage. So the problem here is that the use of public buckets in an access-controlled or multi-tenancy situation is inappropriate. Not only do you have the problem of people may get it from the source of your website, but you also have the problem of one person buys your product with a subscription and then they go and publish the URL on a public forum somewhere. And now no one else has to buy your subscription. They can just grab the URL, paste it into a tool, download all of it at once. In addition, members of one tenant or access control level may be able to access the files in another one. There are a variety of ineffective mitigations I've seen people try to use in order to serve subscription-based content out of cloud storage. There are varying kinds of security by obscurity. There's the giving them long, complicated names and hope people won't guess them. I've seen flash downloaders on a site with referrer checking. So in other words, instead of giving the user the link directly to the file, we serve up a flash app that downloads the file in the background and hands it to them. Well, this will stop your basic non-technical user from seeing the URL, but it doesn't solve the problem of posting on public forums once someone finds it. And if you just run a debugging proxy in HTTP, you can grab the URL straight off the wire when the flash app sends it. I've seen people register a separate domain CNAMEd to their AWS bucket, so their links go to some domain of theirs, and not to bucketname.s3.amazonaws.com. Once again, anybody who can just run dig or any domain tool can look at the DNS record and see what it maps to, and then post it on a public forum. It still doesn't work to keep things safe. The most ridiculous approach I've seen is provide a script on an access-controlled site that proxies the download. And they actually sell these scripts. You can pay a couple $100s to get one of these for your website, where you put a script on your website, so you give the user a link to download.php ? File name, and then on your web server, it uses curl to pull the file down and serve it up to the user. Well, it works. It does keep the file behind the access control, but you've given up all the advantages of cloud storage, because now instead of using the cheap bandwidth out of cloud storage, you've contrived a way to get to pay twice for the bandwidth, possibly 3 times, because your server is downloading it from the cloud provider and the cloud provider is giving it to you, and then your user is downloading it from your service. So it's a great way to pay money for software that makes you pay more money for hosting. It doesn't really make a lot of sense. So how do we actually prevent enumeration? Well, one thing is container-level access control. In Windows Azure Storage, you can actually set a container property that says the blobs are public, but the container is not. This is why there aren't currently any enumeration tools like S3 Ripper out there for Windows Azure Storage. It wouldn't be terribly useful if the developers just set the storage policy to blob only. I'm not aware of any similar setting in Amazon S3. The thing about this, though, is it prevents enumeration, but not URL sharing of files. It means, okay, now someone can't grab one URL off my site and download all my files, but someone can still download all my files and then post the URLs to all of them on a public forum for someone to steal. So it's only a partial solution to the problem. The right solution is to use a private container and make use of Windows Azure Storage shared access signatures or Amazon S3 signed URLs to enforce the access control. This is only a mitigation and not a complete cure, but I'll talk a lot more about that in the defenses and mitigation section on how that can be used to make these sorts of data theft from subscription sites very difficult. So, in addition to writing secure applications, the storage itself has to be protected, because this brings back to the fact that if you're using cloud storage, your database backend is sitting on the internet. Anyone can make a TCP connection to it. It's only the cloud services access control that's keeping them out. So you have to protect the storage account itself. And both Amazon Web Services and Windows Azure use an email address and password as an administrative credential. On AWS, it's an Amazon account, and on Windows Azure, it's a Windows Live ID. In both of these cases, it's things which people use for other purposes. So never use the admin's normal Amazon account that they buy books for, or the Live ID account that they chat with their friends on MSNIM, as the credential for a cloud storage account. These should be treated like a domain admin or root password. This is a high-value credential. What's more, you want to make sure that the email account that's used is an email account where you have complete control of that domain. The problem with this is we have seen cases where entire enterprises have been compromised because someone was using as their central root administrator account a Hotmail or Gmail or other public webmail service. The webmail services that have a password reset, which tells you log in and answer 3 easy questions about me that you learned about on my Facebook, and you can reset my password to something else. And those password resets, when people are using a email address that's used for other purposes, can be used to reset that, gain control of the email address. Once you've gained control of the email address, you then reset your password with the cloud storage provider, and you've now taken control of the entire database layer for a company. Other than using a unique account that belongs to a domain you control, the other thing you can do is use multi-factor authentication where available. And I'll talk about the multi-factor authentication options for Amazon and Microsoft in a bit. So defenses and mitigations. There are a variety of things that you can do to defend your applications. There are the classics of input validation and encoding. If you're using the ASP.NET platform, there's Windows Communication Foundation data services. There are SOAP toolkits and WSDL-based code generation. Encryption plays some role here, although most of these are application-level attacks, and encryption's not going to do you a lot of good there. Multi-factor authentication, shared access signatures and signed URLs, and finally, proper application design and defense in depth. So input validation, all these attacks come from malicious user input. So the first thing you can do is use available blacklist-based platform mitigations. So these are things like mod security if you're using Apache, or turning on validate request if you're using ASP.NET. Now, these are limited. They're blacklists. They're only going to stop the simplest attacks. It's possible for people to evade these in a variety of ways. In addition, you can't use them for everything. You can't use a simple blacklist like this if you actually take HTML input from your users. In addition, implement whitelist-based mitigations where it's possible, where you only allow data types that you expect. Whitelisting, once again, is better for some situations than others. It's really easy to write a whitelist for formatted data types. If you want a zip code or a social security number or a SHA hash, it's simple to write an input validator for that that's whitelist-based. If you're taking XML or HTML input, or if you're writing a Unicode global application where the same app needs to support 14 different languages, it can be a lot more difficult to come up with a whitelist that works and also still allows all the functionality to work right. When it comes to whitelist-based protection, Microsoft Web Protection Library has a set of encoders called anti-XSS, which are a good set of encoders that are well-researched. This is available as a .NET DLL. They're kept pretty up-to-date. It's a great thing to use if you happen to be writing an ASP.NET application. Once again, it's not a universal solution. Not everybody writes their apps in ASP.NET. Encoding is an attempt to render potentially malicious input or output harmless. There are a variety of ways you can try to do XML encoding versus a data storage attack. You could wrap user input in a CData block that will enclose the user input and prevent it from changing the schema. In that case, the only thing you have to filter out is the CData closing sequence, as two right brackets and a right angle bracket will end a CData block. XML and HTML encoding is actually fairly standard. It's not as hard as some encoding types. There aren't that many meta characters, and there are many encoding libraries available, such as the anti-XSS I talked about briefly before. You just have to make sure to not get this encoding confused with the HTML encoding for cross-site scripting. You want to encode output before sending it to the user, and this needs to be separate from your data storage encoding. You need to make sure that encoders you use are consistent and not subject to multiple encoding and decoding. In other words, if your encoder is simply to change angle brackets to some other character, then you need to make sure that you also are filtering out that some other character, or else someone could submit pre-encoded data and your decoder will turn it into an active attack. Encoding is still not foolproof. I wouldn't want to rely on encoding as a sole mitigation. Multiple encoding attacks are very sophisticated. I have seen some here at Blackhat and at DEF CON that are kind of amazing, passing through web application firewalls and the web server level, the database level, all getting interpreted at different ways at different places. If you're writing multi-tier global applications, it's very difficult to get right. So it's important, while encoding is important, there are other mitigations to follow as well. So Windows Communication Foundation is a set of .NET libraries for abstract data access. This is the default interface for Azure Table Storage. If you look at Microsoft samples of how to use it, this is what they're going to tell you to use, as this is the data services layer for the current versions of .NET. Your application uses an object model or link queries to query the database, and then using some classes that you build and inherit, WCF data services translate these into the appropriate protocol. You can use this with any storage backend. It's been being used with SQL servers and so on for a while now. The Windows Azure SDK includes an assembly called Microsoft.WindowsAzure.StorageClient, which provides WCF data services classes for all of the Windows Azure storage services. So the advantage of doing this is if you're using WCF data services, since it's meant to be agnostic with regard to backend, it already takes care of properly encoding things that go to whatever backend you're using. So it knows that it's an XML backend. It properly encodes whatever you're putting in to be safe for XML. As a result, you can consider this roughly equivalent to parameterizing queries. If you're sending your API calls through WCF data services, there's not a way for the text in those values to interfere with the API call itself. I tried but have not found any vulnerabilities in these encoders. I can't get past them. That doesn't guarantee that no one can, but they appear to be pretty strong. The key disadvantages here are really it only works if you use it. Not every application is in ASP.NET. If you're writing your cloud storage app in something else, this mitigation isn't available to you. Also, the developer still constructs query strings. So when you're pulling up items out of table storage by a query string, you do still have to write that. And since that is not XML, but rather just an arbitrary query language, WCF can't really do anything to sanitize it. SOAP toolkits. So Amazon Web Services offer both a REST and a SOAP API. Most developers, in my experience, use the REST API. However, the SOAP API is available, and developers who use the SOAP API almost never construct SOAP by a string concatenation. SOAP headers are very long. It's really quite a mess to construct SOAP by hand, so almost everyone uses a SOAP toolkit of some sort. And these toolkits generate from the WSDL an object model to access the data backend. There are a variety of these available. I know in Visual Studio.NET, there's the System Web Services namespace and the WSDL tool. There are similar things available for Java, PHP, and other platforms. And the generated interface code from the ones I've tried generally performs the necessary XML encoding for you. So if you're willing to take on the overhead of SOAP and use a SOAP toolkit, this can be another way to try to protect your data layer from potential injection attacks. Multi-factor authentication. No, I'm a slide ahead. So encryption. Encryption will save you from application level attacks. Your cloud data endpoints are on the internet, and so as a result, your app's encrypted tunnel to the database will be carrying the attacker's payload. This said, there's really no reason not to use an encrypted transit to your data layer. You're still sending your data over the internet. AWS actually forces you to anyway. Most of their data APIs won't even take an HTTP connection. You have to go over HTTPS. But even if you're not forced to, there's really not any reason not to. You're not paying for compute time on the storage nodes at your cloud provider. You're paying for storage size and you're paying for bandwidth. So as a result, you might as well enable HTTPS. If you're communicating over the internet, that is, you're not hosted in the same cloud provider as your data is hosted in, it's obviously critical. You don't know what's out on the internet that might be snooping your data. But even if you are hosted in the same cloud provider, it's probably still a good idea. The cloud provider is kind of a black box to you. You don't really know what's in their data center. In reality, it's probably pretty good. If you're using a major cloud provider like Microsoft or Amazon, they've put a lot of thought into securing their database and their cloud infrastructure and preventing one tenant from being able to attack another tenant or snoop their data. These are very difficult attacks to carry out. Someone would have to compromise the virtual machine layer and get at the underlying nodes. However, we come back to there's very little reason not to. You might as well encrypt the data. Even if these attacks are kind of far-fetched, there's no reason not to protect from them. So now, multi-factor authentication. Amazon Web Services offers administrator multi-factor authentication via a dynamic password token. There's a nominal fee to purchase the token. It's a few dollars. And then your administrator can't log in with their Amazon account password anymore. They have to use the dynamic token. The disadvantage is there's still one level of access. Either you're the administrator or you're not. So you don't have the ability to delegate this out to a lot of developers. Windows Azure allows developer access via certificates. So this provides you a way to do multi-factor authentication. You can, if you're using Visual Studio or other tools to manage your Azure account, you can put a certificate in there which will allow the developer to use the storage to publish applications, do everything they need based on a cert rather than a password. This certificate can be on a smart card. As a result, you have multi-factor authentication at that point. The developer has to be using their smart card in order to connect to the Azure node. And it's supported by all the Azure development tools. We still have the problem of there's still one level of access. A developer can access everything in the account. You also have the problem of right now in Windows Azure, you can't actually disable the Windows Live ID login. So you can make it extremely well protected, give it a long password, and then have no one ever use it. You can keep it in a safe and use the certificate for everything else, but there's not a way to actually shut it off. Shared access signatures. So these are the right way to handle those cases where you want your users to download files directly out of cloud storage without passing through your service, but you want to still keep it access controlled. So shared access signatures prevent enumeration and unauthorized access to blobs and objects in cloud storage. Amazon calls them signed URLs. Azure calls them shared access signatures. It's the same thing. It's you set the blob or object as private, and then it can only be accessed by a URL that has a certain format which includes a signature. And that digital signature proves that that URL was generated by your application and is allowed to download from that site. So the way you would do this is you would set the blob or object as private, and then your application issues signed URLs accessible in the browser, which are valid only for a limited time and only for a specified object. The user isn't provided direct links to files. The user is provided a link to your application, which generates a signed URL valid for a limited time for that user. If you do this right, it's transparent to the user. The user just sees a link to a file on your site behind your access control where they have to be logged in order to get to it. When they click that link, if they're authenticated, they get silently given a 302 redirect to the cloud storage signed URL. The user doesn't notice any difference. The advantage is that signed URL you've given them. First of all, it's potentially good only for that file. And second, it's good only for a limited time. So you don't run into the problem of them posting it on a public forum and people being able to download from it forever. So here we have an example of that first link would be a direct link to a file that I'm hosting in Windows Azure Storage. And container is music downloads, and the blob name is filename.mp3. So instead, my user clicks on a file on my site, download.aspx music download /filename.mp3. My script makes sure he's authorized and then redirects them to that second link we see there. Now, that second link has a variety of parameters on it. The first ST is the start time. This link is not valid before 11:20 this morning. Second parameter is the end time. This link is not valid after 12:20 today, so it's only valid for a few more minutes. My third is SR equals C says this signature applies to the entire container. So in this case, someone with this signature could also download other files from the same container. I have the option of setting SR equals B, blob level, and then this applies only to that one blob and can't be used anywhere else. SP equals R, I have read privileges only on this blob. SI is signed identifier. This is an optional field that refers to another data store on Azure Storage, which gives me the ability to have revocation. That signed identifier was created by my script at the same time as it signed this URL. And if I programmatically delete that signed identifier, this URL immediately becomes invalid. So if you have a URL that is stolen, you can invalidate the signed identifier, start giving a new one in new requests, and all the old URLs aren't good anymore. Then finally, we have a digital signature. And that's based on the application signature. So it's signed with a private key that the application has that the user has no access to. That signature encompasses all of those fields after the URL, as well as the canonicalized resource, which is either the container or the blob, depending on which I'm giving access to, in a specific format. So if I redirect users to these URLs, once again, I don't even need to show them to the user. It can just be a 302 redirect from my app. They can download the file. They can download the file only for a limited duration, which I have specified. And since I'm doing this from a script, that duration may be, 1 hour from now. I can sign a new URL every time someone goes to download from it. So anytime someone clicks my download link behind access control, they get seamlessly redirected to the file. So they can even still save download links if they want to. They're not going to be seeing the actual URL. But if someone uses an HTTP debugger and steals this URL, they can't really do anything useful with it. It's only good for the next hour. Posting it on a public forum doesn't do them any good. Once again, it's not completely foolproof. Yes, I can copy all of these URLs and post them on a public forum and say, quick, everybody, download it in the next 20 minutes. But it's going to make it a lot more difficult for subscription-based files to be accessed. If you really need very tight access control, I am going to check every single time someone downloads. Then you may not be able to take advantage of the cheap bandwidth of cloud storage. You may actually need to put it on a hosting with actual programmatic defenses. So secure application design. This is a little more general than the cloud storage API specific stuff I've been talking about, but defense in depth. Use multiple layers of defense, keep compromises isolated, and prevent elevation of privilege. So when you're writing an app using cloud storage, consider the layers of protection and use cloud equivalents of traditional defenses. We can also do some things to design the application for security. So if we've got a cloud application, we really have multiple layers here. We have the service layer, that's my product, security architecture, and compliance controls, and code qualities, and my using platform features. But then under that, we have the platform layer, which may include runtime privileges and code access security trust levels if you're using Windows Azure hosting. No matter what you're using, it can include user accounts, isolation, operating system privilege levels, making sure that your applications run with limited privilege. So if an application is compromised, it can't compromise the entire server, access crypto keys, etc. And then finally, at the lower layer, you have the infrastructure layer, which gives you your service scale out and the ability to expand your service quickly. So mapping traditional defenses to the cloud. Things like input validation, sanitization, fuzzing, the things that are truly application level, there is no change. You need to do exactly the same thing with a cloud application that you need to do with a traditional application. However, other things do have some changes. Application level DOS protection, you instead have things like application level request throttling or automatic scale out to defend with these things. Authentication, authorization, and audit. Many times the cloud providers will provide services that you can utilize. So for instance, there's Active Directory Federation services, Windows Live ID. There's also, for audit, there's sometimes tracing functionality. I know Windows Azure has tracing functionality where they have a audit store available to applications. For ACLs on your storage, we instead have the shared access signatures. For certificate services, storing certificates can be difficult in cloud hosting because where do you put them? You can't really put them in the you don't really want to put them in the image for your application if it's going to be scaling out. Windows Azure provides a certificate service where when your application boots up, the platform itself installs the certificate over a secure connection. And for inter-process communication, you have things like internal endpoints and the aforementioned queue storage. So there are equivalents to the defenses and defense in-depth measures you would normally use. It's just a matter of learning what those equivalents are and making sure that your application utilizes it. Oops. So defenses inherited. When you're in a cloud hosting provider, it's not just infrastructure. With Windows Azure, especially with it being a platform as a service offering, you have not only the infrastructure things, but also things like certificate services and but many of these things would be true with any cloud hosting provider, with things like hypervisor sandboxing and load-balanced infrastructure and network-based protections against denial of service attacks, and whatever protections that they give you at the virtualization layer to protect your VMs from other VMs. So I don't have a lot of time left, but I'm going to talk briefly about design patterns for cloud applications. So one other thing that can always be used is the security development lifecycle. It's applicable to really any cloud application. When we find people inside Microsoft developing cloud applications, they usually use the SDL for Agile because they tend to be online services doing rapid releases. The Microsoft SDL site covers SDL for Agile in detail. We mandate this for any internal applications that's deploying to Azure. Obviously, it's just recommended for external customers. People can host whatever they want in a cloud provider. But we do recommend it to be used by anyone to develop more secure applications. Appropriate design patterns can take advantage of Azure runtime trust models to create hardened applications. This is talking not so much about cloud storage as if you're actually hosting your application in the cloud as well. You can isolate web roles and separate duties to individual roles to maximize use of partial trust. With a Windows Azure application, there's a locked down mode for your app, which has it run with lower privileges. And if you set your externally facing web roles to a more lockdown state, then it restricts access to the file system, registry, local environment, and so on. So a gatekeeper pattern is something like this. Your customer communicates with a web role running in partial trust, and then that web role only calls services on a worker role back behind it. And that may be through queue storage or through an authenticated web service. The important thing is it's a restricted interface. There's only some things they can send. And it is accessible only to the application. It's not available outside. Then any of your storage requests are done by this worker role. So by separating these things into a privileged backend worker role and another role which services requests from the internet, we get the same sorts of things you would get with a multi-tier application in a data center. Your backend takes inputs only via a secure channel from the gatekeeper, and it handles sanitized storage requests. Ideally, it will also do some checking, because if someone fully compromised the front-end web role, they could be sending malicious requests back through. So you've got 2 layers of checking. However, there's very little interface to this. All you can do is send your storage requests to it. As a result, you can only do data operations that are intended for the app. For instance, if your application only retrieves customer records one at a time and has no need for a get all customers call, there's no reason that your keymaster role needs to implement a get all customers or make arbitrary data query command at all. It may only implement get customer by customer ID. At that point, your attacker is limited in what they can carry out, because they have a very small attack surface on a privileged role which has all the data keys in it. Also, they've not gotten any of the keys to your data by compromising the front-end role, because the keys aren't there. In addition, if you needed to run anything with full trust, with native code execution, you could run it on this back-end role to keep the front-end role as unprivileged as possible. Now, while I've described that in the context of Windows Azure, because Azure facilitates that design pattern with the 2 trust levels, there's really no reason it would be restricted to Azure. You could implement a design like this anywhere, including Amazon Web Services, cloud, or even a non-cloud platform. The point is to separate your presentation logic from your storage logic and create a restricted boundary between these tiers. Really, it's the equivalent of the approach of making all of your database access through stored procedures and giving your application exec-only permissions. So the only things your app can do at the data layer is send precisely formatted queries that are doing the kinds of things your app does. If your app doesn't need to drop tables, there's no reason for it to have access to. If your app doesn't need to be issuing arbitrary queries, it doesn't need to have that ability. You configure least privilege on each tier. In addition, when you're threat modeling back-end tiers, do it under the assumption that the front end's already compromised. Your front end is across a trust boundary. Even though you don't mean for it to be a trust boundary, it is one. So, in conclusion, security is an important consideration in the cloud, and the work required to secure an app in cloud storage isn't really new or more technically challenging than a traditional database environment. I don't really want to convey the idea that it's more dangerous to use cloud storage. It's not necessarily. There are a lot of security features available to you if you use them. But designers and developers must consider the threats to their application and follow appropriate practices for cloud storage. And you have to use appropriate secure design and implementation patterns to counter threats that you may encounter in a cloud environment. All right, thank you.